right, well, welcome back. This is segment 2, and we're talking about building construction as it relates to collapse, and also how the Florida Trust Law, these emblems here, come into effect as far as fire operations. We just watched a video about an incident in Green Bay, Wisconsin, where a firefighter fell through the floor and into the basement. And we'll be looking at other video of tests where they have performed these various tests on the structural components of these floors, the joists and the trusses and so forth. And they're going to refer a lot about basements. Of course, in Florida, we have very few, if any, basements, so it's not a huge problem for us, if any problem at all. But you just need to transfer that image to any time you're working above the first floor of a fire, be it in a residential, single family, or if you're in a multiple residential or any commercial occupancy where you're operating above the first floor. That's going to be our similar situation. So I don't want you to get off track like, well, they're talking about basements here, and we don't deal with basements. So with that said, let's take a look at what we have here. We have a video that will show the older style construction that we've talked about, and it'll show us a fire condition onto this support system for a floor. They're going to be using 2x12 as joists, what we call dimensional lumber. But also keep in mind, this video, they were doing these tests, probably saving as much money as they could. So you're actually going to see OSB board for the floor decking, and that wouldn't be the case in the older days, in the 60s and so forth. That would be probably a tongue and groove flooring, something of that nature in that day. At the very least, it would be 3/4 inch plywood, not this OSB board. So don't be fooled by that. So we'll take a look.
This structure represents more of the older style construction methods in that it's using solid joists. These are nominally 2x12s. They're 16 feet long. We have a 16-foot span here. Above that then is the subfloor, the oriented strand board, and that's the same in the rest of the structure. So the only real difference here is the support beam that we're using. And again, this is somewhat characteristic of older style construction methods. This has this sawn lumber, if you will, nominal 2x12 joist, 16-foot span. So we tried to only vary one thing between each experiment. The subfloor is the same, the wall material is the same, the fuel load was the same. As you can see, we still collapsed out of the center where our static load was, because that's the portion we're stressing. But here you can see that, we've got some of the joists here intact on both sides of the collapse area. They're damaged, they're charred, so their load handling capacity has been reduced significantly, but right now they're still up and in place.
This shouldn't fool firefighters, though. We still have a hazard.
So just because this is older, more traditional construction, firefighters shouldn't feel a false sense of security about coming in here.
No, not at all. We still have some of the same hazards. We still have some collapse. Yes, it's lasted longer, and Dan's points are right on target. But if we add burn time to it, if it's taken longer to get here, if it's been burning longer before detection, we still have similar conditions. Be it old construction or new construction, we have to understand what we're getting into before we commit our personnel to operate in site.
Okay, as Chief Goldfeder said, that it burned longer and so forth and so on, and that's the key, as we talked about. Time is the key. So that dimensional lumber will burn longer. So let's take a look at some pros and cons. Let's take, for instance, if we're sitting in a 2-story house that was built in the 1960s. We already discussed that we're going to use dimensional lumber for floor joists. So let's just say we're on the first floor and the bedrooms are upstairs. And above our head here, we have plaster and lath for a ceiling. And then we have these 2x12s every 16 inches that are supporting the floor above us. Right? So we have however many of those supporting this area. Let's say there's 12 of them. So every 16 inches we have this open bay above the ceiling and below the floor. Okay, 12 or so inches open there. And let's say if we had a can light up in that ceiling there, and there was a malfunction or whatever, and that can light started on fire, and it started a fire up in that area, burning the second floor, which is tongue and groove, and the 2x12s on each side as the fuel. What are some of the advantages of having those 2x12s there versus some other components? What would an advantage be in this bay here that has plaster lath and tongue and groove on the top? as far as fire spread and so forth? What would be an advantage? Yes.
Reduced oxygen?
Okay, there's going to be reduced oxygen. There's not a lot of areas that can pull any oxygen in. Anything else?
Burn time to get through it?
Burn time to get through. For it to burn through a two inch, and back in the day, of course, that was a real 2 inches. You know, in the 60s, it's 1.75 inches, but back in the 40s and 30s, that was a full 2 inch by 12 inch. So burn time to burn through that. Anything else? Okay, it's compartmentized, right? It's really not going to go anywhere. It doesn't have the oxygen, and it's not going to be able to burn through those 2-bys very easily. So that is certainly an advantage or a pro. The con is that there are some components that can burn and so forth, so you still have that there. But the main advantage of that is you have a lot of beef to burn through, and it's compartmentized. Now, what about if they had to run wires? Here's your joist going this way every 16 inches, and they had to run a wire from there to there. How would they run that wire? Back in the day, they'd get a 1/2-inch drill bit, and they'd drill a 1/2-inch hole through that 2-by, a 1/2-inch hole, and then they would put the piece of Romex wiring through the hole. So it basically takes up the whole space. They're not using a hole this large to put a wire through, because if you did, then you would have some additional oxygen, be able to fire travel through these voids. So you really didn't have any penetrations through those that were substantial enough. They're not running 6-inch ductwork for air conditioning, drilling an 8-inch hole through there. Okay? They're going to go around that. They're going to design it differently. They're going to run it this way and put a vent or whatever. So the advantages, disadvantage of that is apparent here. Let's take a look at the next one. Here's your engineered I-joist. Keep in mind, this is not a truss. It's just another lightweight component, and we'll look at the differences.
In this building, we're using wood eyes as the floor support. The wood eye is composed of sort of 3 basic components: a top portion, a bottom, and then a bottom flange, and then a web in between. The top and the bottom are made of a plywood type material or a laminated wood material, and then the web portion is constructed of an oriented strand board type of material, very similar to the flooring that we have above it in all the structures. In our experiment, what we're simulating is a fire in a basement. Well, basement walls typically are made of concrete or concrete block, and they will not be the point of failure. We don't want the fire burning through the wall. So to accomplish that with our simulation here in our test mock-up, we've got 2 layers of gypsum board. We've doubled that, doubled what you would typically have on a residential wall, so that we do not burn through that first. We've got our thinner elements in the roof, or in this case our subfloor section. We're channeling all our heat up there. We've got the fuel centered under the span, and we have our weight directly over that. So we're, by design, influencing where this collapse will occur and trying to, again, replicate that as we go from structure to structure.
So this is the first building that burned. What is it that you've learned from it?
Well, from a firefighting standpoint, let's just look around. Look at the floor. Okay, we've got floor collapse. Okay, so this draws home the point to firefighters of what they're walking into. What's remaining on the wall that had collapsed in and folded down, some of the things that have dropped through. On the bottom side, it was on fire. It was burning. It had temperatures close to 2,000 degrees. But on the top surface, the temperatures were still relatively cool. I want them to understand how thin this is, how combustible this is, and this is designed to hold people and furniture up when the house is not on fire. When the house is on fire, it's a completely different dynamic. And we don't think about that sometimes, and we have to.
Hey, a couple key points there, as Chief Goldfeder said. Those do perfectly fine holding up people and furniture. That's what they're made for. It's under the fire conditions that there are problems, and they're not designed for that. So that's a key point. The other key point is that the surface temperature on top of that carpet on the room above, and he didn't really pinpoint it, but I've seen video from the UL testing. The carpet temperature would be 102 degrees, and underneath would be upwards near 2,000 degrees. So if you're crawling around on the second floor searching in a bedroom, and there's fire below you raging, you're really not going to notice the heat. Okay? Now, keep in mind, these are in a lab test facility, so it's not 100% what we're up against. But I don't want you to be fooled like there's no way I would be above that fire. I'd be burning up in there. No, it's not the case. Okay? Especially if it's venting out windows down below. Okay, it's venting out the windows down below, it's taking care of that issue of where's this heat going. So, let's take a look at the pros and cons here. All right, same situation. We're in a 2-story residential structure or apartment, doesn't matter. And now, instead of those 2x12 joists, we have the engineered I-joists. Right? Advantage is we still have the compartmentalization there of that bay being enclosed in. The disadvantages are, even with the solid I-joists that we saw, they have knockouts for running utilities and so forth. We'll get to that, but let's just say it doesn't have knockouts, it has no penetrations, it's just the solid I-joist. So we still have the compartmentation. The differences as far as negative are that now how much needs to burn through for fire to travel to the next bay? How thick was that web member? Half-inch. Half-inch OSB board. It's not even plywood. So instead of 2 inches needing to burn through, in 6 minutes, that can burn through. We'll see a test here in a minute. I think it's 5 or 6 minutes, that web burns through, so it travels to the next bay over, and so forth and so on. So the other issue is, what is our ceiling now when we're using these lightweight components in the year 2000, 1990s, 2010? What is the ceiling now? Is it plaster and lath? No, it's going to be drywall. That drywall is going to fail in about 15 minutes, as we'll see with some testing, and then fire can attack these engineered I-joists that are holding up the floor above. So, pros and cons. There's very few pros left. Now what about when they want to run a wire through there, what do they do? If it's just a solid one, they'll drill a hole, I don't know what size hole, or they'll take a hammer. Boom, anybody in construction knows it. Take a hammer, that's OSB board, I'll punch a hole right through that with a hammer. Now you might have a hole this big with a wire this big, so you do have some issues with it drawing oxygen from the other bays and possible fire spread. Or they have the engineered I-joists that have knockouts. They're perforated knockouts. So it'll punch out a 2-inch hole and run a 1/2-inch wire. Or they have 6-inch, 8-inch. I have a chart that shows, depending on the height of that I-joist and the length, it tells them how large of a hole and how many holes they can put in there to run the utilities and so forth through there. So that's the con, that now you can draw oxygen from other bays, if you will, compartments, and the fire's going to travel. And the more fire that gets up in there and starts eating up these I-joists, the less success you're going to have upstairs of maintaining an environment that's not going to collapse on you. Now, with the other ones that we already looked at, they have the pre-cut holes and so forth. We'll watch a video here, and we'll take a look, and it's quite obvious that as it gets lighter and lighter and lighter, there's going to be problems. All right, first we'll watch a newscast of some incidents that have happened with these I-joists.
In a fire, something inside your home could pose a deadly risk for firefighters and maybe for you.
Tonight, 12 News uncovers the danger that may be hidden beneath your feet. Kent Wainscott is here with the results of an exclusive 12 News investigation.
And I want to show you something. This is a common manufactured wood I-joist. If you live in a newer home or you've had some extensive remodeling done, chances are you may have beams just like this holding up the floors in your home. It's lightweight, strong, and inexpensive to use, a perfectly good building material. But it has one very serious flaw.
He grabbed my strap and started dragging me toward what he perceived as a light source.
Milwaukee Fire Captain Ted Stribling lay unconscious and badly injured inside a burning home. The last thing he remembers was walking into the blaze alongside fellow firefighter Tony Rueda. He has no memory of what happened next.
Tony and I fell through the floor. Tony did not lose consciousness, and he rescued me.
The floor beneath their feet gave way, sending the two firefighters crashing to the concrete basement below. When he was pulled from the blaze, at first glance, firefighters thought Stribling was dead. But thanks to his colleague, both men escaped, injured but alive. Days later, when Stribling returned to the scene, he noticed something alarming.
And what I could see from the underside was these wafer-thin I-beams made of composites of wood and glue.
The older home had been remodeled with newer manufactured wood I-joists, like this one, supporting the floor.
Manufactured trusses, all along here, and they're all gone. The bottom plate's gone and the middle plate's gone.
Following the blaze, 12 News went inside that home with a Milwaukee firefighter and saw up close why those floor beams failed when the firefighter stepped on them.
One of these on top and one of those on the bottom. And they just burn up and separate.
They're perfectly good construction materials. They can make up just a fine home. The problem with them is they burn really quickly.
So quickly, in fact, that they've proven deadly for many firefighters. It happened in this Green Bay home in 2006. A veteran firefighter was killed when the floor collapsed below him, trapping him inside the blaze. And this is how a Department of Homeland Security report describes what happened last year when a Tennessee firefighter crashed through a hole in the floor of a burning home. A firefighter who had been behind firefighter Sean Doty reached down into the hole but was unable to reach his hand. Firefighters made contact with him but were unable to retrieve him. Firefighter Doty's remains were recovered after the fire was controlled. The floor that failed was constructed with engineered lumber.
There's very little warning time. Floors don't tend to sag before they fail, and so firefighters are being caught very much off guard with this type of failure.
Dr. Tom Schley is a fire instructor at Waukesha County Technical College, and he and his staff helped us demonstrate the danger these manufactured beams can pose to anyone in a fire. We lit a flame below both a manufactured I-joist and a traditional solid wood board, put a weight on top, and watch.
All right, we're just 20 seconds into this. You can already see some charring begin here, much more so on the manufactured wood.
The difference was noticeable from the start. Within 5 minutes, a hole began to form in the center of the I-beam.
All right, we're 13 minutes into this blaze right now. The two cords, the end pieces of this I-beam, are still intact, barely. But the area in the middle, known as the web, you can see has long since burned away.
At this point, just the bottom piece of the beam is all that's supporting the weight above it. And then moments later, it's gone.
All right, less than 15 and a half minutes into that blaze, you can see this board failed, the manufactured wood, while the solid wood is still strong enough to step on.
15 minutes and 21 seconds after the first flame, perhaps just the time firefighters might be entering a burning building.
They'd be possibly doing search and rescue, maybe making an interior fire attack.
In my job, when you see a house, you look at it and try and imagine what it's going to look like when it's on fire. And these houses will burn really fast.
That's the danger, one which might force firefighters to reassess how they battle a blaze, to take a more defensive approach, and perhaps take less risk entering a building. And that could pose a danger to anyone.
It's not just firefighters that are at risk here, it's homeowners too.
It's the general public that has to be concerned, because that means the building might burn a little bit longer because it's going to take me that much longer to get up that staircase.
So, what's being done? Well, we checked with the Metropolitan Builders Association of Milwaukee, who is aware of the concerns that these beams can pose in a fire. They tell us that the building industry takes fire protection very seriously and that the products that they use meet all building codes. They also say that the industry is currently investing in research, working to develop new fire-resistant building products, and is working to educate firefighting agencies on how best to fight fires involving the most common building materials used today. Firefighters, meanwhile, tell us this is a hazard that they simply have to be aware of and prepare for, so that when they respond to a fire, if they think that the building materials being used are the kind that are going to fail more quickly, they are just going to have to take that into account when they decide when and how to enter a burning home.
And what about the homeowners? Is there anything that can be done to make this safer?
Yeah, not the beams specifically, but some fire officials say residential sprinklers are a great safety tool. But really, the best advice for anyone is just practice good fire safety, because, you know, these beams can pose a hazard several minutes into a home fire after the fire breaks out, but by that time, smoke can be the real problem and even greater danger. So bottom line, make sure you have a good working smoke detector and a good escape plan. Hopefully, if there's a fire, you're out of the house before the floors fail. Unfortunately, firefighters are often going into the home at that time.
Very interesting information. I'm sure there'll be a follow-up. Thanks a lot, Ken.
Okay, good point from a reporter. They're just going to need to take that into account. So when you know these systems are in place by these signs here, it's just another tool to take into consideration. It doesn't mean we don't do this or don't do that. It's just one more little piece of the puzzle to put together. Now, I'd like to correct the one fellow on there called that a truss. So I want to make sure we all understand it's not a truss. Now, what does the industry have to say about it? Well, the industry doesn't deal with any fire issues, but just for showing you what's out there, these are the new XJ85s. So let's take a look at the industry video.
Back in the days when dinosaurs roamed the earth and rocks were soft, floor and ceiling joists were made from solid sawn lumber. This brought with it a few challenges. The boards were never exactly the same dimensionally, and they had a tendency to move around and shrink after installation. Squeaky floors and other callback items caused more than a little distress with builders. Then came the engineered I-joist. It solved a number of problems and has remained pretty much the same until now. At a recent home builders show, Georgia Pacific introduced their XJ85. It's what they're saying is the first engineered I-joist with pre-cut openings for HVAC ductwork and plumbing. The product makes a lot of sense from an energy-saving standpoint, because it allows the builder to run ductwork and other components through conditioned space. So instead of fighting harsh attic conditions and losing thermal efficiency, ducting can more effectively do its job of transferring conditioned air from the main unit to various rooms. The joist also eliminates the need to cut openings on the job site, which may or may not weaken the structure of the joist. Anyone who's ever had an inspector look at a site-cut I-joist with a critical eye knows the value of this aspect of the product. Because the structural stability of the XJ85 has been engineered in, complete with openings, it's a simpler, more cost-effective building product to use in just about any job. Combine all that with the fact that this joist is NAHB Green approved, and you've got a real winning combination. Check out the XJ85 engineered I-joist with pre-cut openings for your next project. Complete information is available on GP's site. For HGTVPro.com, I'm Brad Staggs.
Okay, so we used to have the advantage, at least if we knew it was an engineered I-joist, we at least had the advantage of some compartmentation. So that's gone with these. If I was an inspector, a building official, or fire marshal, I'm seeing a system of repetitive triangles here. I would tell them that's a truss, we're going to mark this building, even though we wouldn't have the latitude to do it with the solid web truss. But this one, like I had mentioned, with the truss law, we're only asking a person to put a sign on their building that costs $10. We're not asking them to retrofit with a $20,000 sprinkler system or anything. So I would take a look at that as an inspector and say, hey, I see a repetitive system of triangles. I think that's referring to a truss there. Okay? But we lose the compartmentation. Now it's all open, like an open web truss, which we're going to look at in a couple minutes here. Here's an incident that just happened. This just came across the wire the other day. Urbandale, Iowa. You can see the engineered I-joist, how they're burned through. In this particular case, the fire started outside. It was a situation where they were barbecuing with some charcoal and didn't dispose of the charcoal properly, or thought the charcoal was no longer burning, and the fire went directly into that void space and into the truss area. Into the joist area between the looks like a sub-basement and the first floor on this 2.5-story building here. You can see here is a picture of the bay or the compartment and the damage within to those engineered I-joists. Next, we'll take a look at open web parallel cord truss being used as a floor joist. So this is a true truss.
Now we have an opportunity to look at a building that's a little bit more advanced in construction.
This is called open web joist construction. Basically where lumber is fastened together using the stainless steel gusset plates, and it provides an open space between the top and the bottom of the joist. It's not a sealed unit like we looked at some of the other construction. So what is happening is this provides an open void above the ceiling for fire travel. And it's also for all mechanicals. So when you look at the space now, it's wide open. It's easy for the construction people to put all the mechanicals in. The electrical, plumbing chases, HVAC systems are all up there. All these materials are combustible. And there's no fire stopping in this like we saw in the solid joists or in the TJIs. This is all open. So once we have a fire into this space, the rapid expansion and propagation of the fire goes all over. Now you have basically, you can have the whole underside of the floor on fire at the same time. So this is another extreme hazard. This one is ready to be closed up. This needs to be documented. The fire department needs to know what is above their heads, above the drywall or the gypsum sheet board in the ceiling, so they can understand everything that's burning over their head or could be burning over their head and the reason for the collapse. Because the gusset plates, the steel gusset plates that are used to hold the hangers together under heat and stress, and as the wood starts to char, they will literally pop out, and failure can be almost imminent as a result of this type of construction. The other thing that we're really concerned about is the open expanse that these provide and the additional fuel loading that is put into these.
Okay, he said collapse can be almost imminent. Collapse is imminent if it continues to burn. Sooner or later it will collapse as long as there's enough fuel. So when we look at the pros and cons now, same situation, except instead of having 2x12s or I-joists, we're using parallel cord trusses. Most people think of trusses as roof support systems, but they're used a lot of situations for holding floors up also. And we're concentrating on floors for a reason. Of the injury and death to firefighters due to collapse of buildings, the number one is going to be floors collapsing, number two will be roofs collapsing, and number three will be walls collapsing. So floors is number one. But just keep in mind, these truss systems, we're talking about roofs as well as floors, although we're concentrating on floors here. So if we have the same situation, we're in this two-story residential, and what's holding up the second floor is going to be these parallel cord trusses. Now what are the pros and cons? Well, there's not too many pros left now. This is wide open up there, and everything's running through there, as well as a lot of electrical connections and electrical appliances like the top side of lighting and so forth. So there's a lot of ignition sources available, and it's wide open, and fire can spread throughout this area. In addition, on the downside is keep in mind that when a truss is built, every component of that truss is engineered to do a job. So you have a cord, and webs. If you lose a web, that truss just lost strength. It might not be enough for you to go through. But if several of those cords or several of those webs are compromised, then you have a problem where you could go through. You don't have to have an entire assembly collapse to get killed or injured. There's a firefighter named Nance that was killed some years ago. He was about 5'7", and there's now a drill, the Nance drill, because he fell into a basement and they couldn't get him out. He fell through a hole about that big around. He fell through a hole so small that when they put a ladder down to get him, he's alive down there, and he tried to climb up, he couldn't get out of the hole because it wasn't large enough with the ladder in it. So you don't have to fall through a giant hole or have the whole floor collapse. As long as you're that hole's big enough for you to go through, that's all it's going to take. So as far as the open trusses in the floor space, or you could take it into thinking about an attic also. Remember in fire school they taught you about the surface to mass ratio and how fire deals with that, okay? Right? So the more surface area you have, the more fuel you have. I'll give you an example. If I take a case of paper, I don't know how many are in a case, but it doesn't matter. I get a case of paper and I set it on the table and I try to light it on fire. You're going to get some flamage on the outside there, some flames and smoke and so forth, but you're not going to have a violent fire. It's going to be very hard to burn that case of paper because of the format that the fuel is in, right? Now I take that exact same case of paper, and during lunch hour, I take each sheet of paper and I throw it in the corner. So however many pieces are in a case, 5,000 we'll say. I got 5,000 pieces of paper over there in the corner. Now if I go light that on fire, what happens? You got a heck of a fire. It's the same exact fuel, it's in a different format. All right, now let's relate it to what's above our head here. Now we got all this surface area, all these trusses up there, every 2x4 is exposed. And that's the problem there, because you have all that area, you have the enough oxygen to feed that fire till it burns through and gets more oxygen. So these are some issues that you should be thinking about when you're looking at these various designs of joists and so forth. This fire happened in Parrish, Florida. For those of you who don't know, it's in Manatee County out east, a very rural area, although they do have a paid fire department now on duty, at least in the daytime. I'm not sure if they have 24-hour coverage, but this happened while firefighters were on duty, a couple miles from the station, afternoon fire, and you can see the tremendous amount of damage that occurred to this house. It's a fairly new house, new neighborhood on that road going out to Fort Hamer is the area. So what occurred here was a collapse, a total floor collapse with the firefighter upstairs. The only reason you didn't read about this in the newspaper, or the people in Chicago didn't read about a line of duty death, is because the floor collapse happened during overhaul. If it would have happened during active fire conditions, it would have been a much different, worse outcome to that firefighter that fell. Actually, the firefighter was operating in this area here and rode this collapse on down. Luckily, the fire was already knocked down by that time. But you can see here the truss components here. This is a parallel cord truss being used as a floor joist like we just looked at. You can see deep in here. You see the triangle, see the gusset plates? All right. Now what happened here, and when I talked about ignition within this space, is they had a dryer at the back of the garage. There's a room. It's the washer and dryer laundry room. And from the back of the dryer to the outside of the house where they want to vent the lint pipe is like 25 feet or something. Well, if you read the directions that come with the dryer, it says you can't duct this for more than like 14 feet because it doesn't have enough fan to be pushing all this air. So there's a device that you can buy that is in line in the vent pipe. It's a little booster fan. So the little booster fan was halfway from here to there, like at the 12-foot point, is this little booster fan. Well, that's up in this void space between the floor and the ceiling in the trusses. And it's an electric fan. Well, what happened was the outside vent, little louver thing on the side of the house, it didn't go out the roof, it went out the side of the house. The stucco guys were sloppy, and the stucco held most of those louvers down. So when they were venting they were probably wondering why their clothes weren't drying so well. But in addition, the lint wasn't going out. And we all know that some lint gets in that pipe. You can go in any dryer vent and reach your hand in there and pull out a ball of lint. So it built up on that fan, and that's where the fire started, in the void space. And so the most damage was within the void space of the trusses in this particular fire. That pipe is right there. Now another, well, I read a lot. In another case history, in Chesapeake, Virginia, firefighters went to an auto parts store fire. Okay, so the auto parts store employees smelled smoke. And so this is your typical discount auto parts in a strip mall. Right? You got the acoustic ceiling tiles, and upstairs they had wood trusses holding a flat roof. And so they smelled smoke, and they didn't know where it was coming from, so in order to not smell smoke, they opened the doors, which it was a windy day, so that introduced more fresh air into the store. Finally, it got so bad they called the fire department. Fire department got there. What do you think they saw on arrival? Nothing on arrival. So they started poking around, looking. Now they start getting some smoke and so forth out the back, from the crews in the back. And I remember the exact minutes, but it was like less than 10 minutes. The entire assembly collapsed and killed 2 or 3 of them in that store. Okay? Because the fire started in the void space, and it started in a electrical component above the bathrooms. Don't recall if it was a hot water heater or electrical connection, but it started in that void. The most damage was to the trusses, and the trusses dropped on them. So keep something in mind. You got steel bar joist trusses and these metal trusses, and you got these wood trusses. The wood trusses add fuel. The steel bar joists may expand, and they'll still fall on you, but at least you're not adding to the fuel load. So that was another incident. The incident that the truss bill is named after, the Aldridge-Beng Firefighter Safety Act, is Todd Aldridge and Mark Beng, or Benge, And those were the two guys that were killed in Orange County, Florida, at the gift shop fire in 1980, late 80s, where within minutes of arrival at a fire in that attic space, lightweight wood trusses came down on and killed those two. There's video and pictures of another guy escaping out a back door that was, it was a glass panic bar door that was chained shut, that he had to bust through the glass, and he's coming out. The straps on his air pack are melted off, the pack's hanging down here, and so he barely survived that, but it killed those two guys. So I can go on and on and on. I could read, you know, there's case histories all over the place. So we want to do what we can to make sure that we're not on or under a truss when it collapses or a floor joist. So let's take a look at a summary.
We love being firefighters. It's kind of the way we are. So we have to, if we love being firefighters so much, we need to do what we can to preserve ourselves so we can keep being firefighters as long as possible.
Why is it important to come through a development as it's being built so you can see what's going into the homes?
When we think about pre-planning or pre-fire planning, we think about commercial buildings, schools, institutions, things like that. We don't often think about residential, single-family, or multifamily dwellings. But yet that's where we're going on most of our fires. So while firefighters think, well, we can't get into people's homes, we really can. By establishing a quick relationship with a local developer or a local builder, odds are they're going to let the fire company in, take a look around so we can see what's going on inside these homes. And generally, if you hit a new neighborhood represents, one home will represent pretty much most of the homes in the community. And it gives you younger and less experienced firefighters an opportunity to see what's going on.
The two of you are coming into this home for the first time. What are the first things that are catching your eye?
First things that we're looking at in this type of structure is the newer methods of building construction, looking at the type of materials that is being used. In the walls, we're looking at walls, ceilings, and floors, just to know basically what the flammable characteristics of these products are going to be. We're looking at how they're put together, how supports or ceiling supports are fastened, the types of joists that are being used, the types of subflooring straight that is being used. In the older homes, there used to be a double lap on the floor overlap, and you could burn one level off in a basement level, and from a basement fire, and you still have a good another 3/4 inch of solid wood above it. We're looking at how those failures can occur within a modern structure, or how it may occur, how the walls may move, how the joists are hung as compared to some of the old construction. Now, in this particular house, we're looking at a ceiling that is basically the same as the floor that we're standing on. So in this particular structure, we're not looking at solid wood joists. We're looking at composite construction. We're looking at a top and bottom stringer with a solid web that is made with oriented strand board. It provides extreme vertical strength, and they can do long spans with these things because the way they're put together, they will hold more weight and more span.
So when fire companies arrive on the scene, if the incident commander decides to deploy companies within the building, and in this case, notice we got a poured cement floor here. So we don't have the concern about falling into a basement. There is no basement. However, if we've got a fire, say, in the kitchen, as the chief was talking about before, and we've got fire spread up into this void space here, companies have to get in. They have to use the thermal imaging cameras. They have to use tools. They got to open up and find out where that fire is and get water on the fire. So it's got to be, as we've discussed throughout this entire program, the need to pre-plan, understand what we're dealing with, and then have the incident commander arrive on the scene to determine what the life hazard is, what our resources are, our people, our equipment, our response time, where the fire is, where was it, where is it going, get to it, pull the ceilings, pull the floors, pull the walls, whatever we have to do to get there, if we can do it for a reason.
All right, so Chief Goldfred is talking about pre-planning and being able to get into these places while they're under construction, which I've never been on a site that a contractor or superintendent said, no way, you can't come on the site here. I've had them in there, hey, if you grab a helmet or a hard hat, that's fine. Now keep something in mind. The building boom, which ended a few years ago, will be back sooner or later, maybe not as aggressive, but back in the 2004, 2003 area, in that time frame, you had tremendous growth in your county, as we did. And if you go into a neighborhood, let's say it's a single-family home neighborhood of 3,000 square foot homes. You can go in there, and if it's all built by one developer, like for instance, there's one going in right now called Central Park in Manatee County. It's built by Pat Neal. If you go in and look at one home and the components being used, and you go down the block, 12 houses, what are you going to find in that home? You can find the same components being used. So I can lock that away, or I can put it on a tactical plan. Central Park is built all with engineered I-joists for floor supports and wood trusses for roof supports. Now, if you go out further to where I live in a place called Mill Creek. Now, Mill Creek there's still some phases being developed, but the difference is you can hire anybody you want to build your house, or you can build it yourself. So now you can't apply that same to that neighborhood, because different builders are going to build different. And we're not computers, so we can't, go in and lock it away. Okay, 1418 was made of this, and 147, we don't do that. So how do we find out? When we're called, we get to the fire, you get a knockdown on the fire, and the chief's wanting to know, is there any extension? So you need to pull ceilings, pull walls, whatever, to find out if there is extension. And if there is extension, the chief's going to want to know, what is it extended into? Is it solid dimensional lumber? Is it an engineered I-joist? Is it a truss system? And that's all filed away for making decisions as this event unfolds. So keep that in mind. You can get out in these neighborhoods, but don't apply that same to all neighborhoods. It all depends. And for your tacticals, you just got to put it on your tactical. Like I say, there's too many buildings. We're not going to remember all the various buildings. You have a tremendous amount of apartment complexes in your county that are 2- and 3-story garden apartments, and these are going to be loaded with this type of construction if they've been built in the past 20 to 30 years. All right, along the same line here, what's wrong with this picture? What do you see as a problem there as a tactical plan, looking at that building right there, that strip mall, which is very common in our counties? What do you see there, that kind of little red flag to you? Where don't you want to be operating when that's on fire?
Underneath that.
Underneath that facade, yeah. Okay? Because that's a cantilever facade of some sort. There's no column supporting that thing there. So what do you think happens when that store burns? What do you think is going to happen to that facade? Okay, when it burns like that right there.
It's going to fall.
It's going to fall. Career firefighter dies, the chief is injured when struck by a 130-foot awning. They call it an awning. It's a facade that's supported by, what do you think? Lightweight components. It's supported by hybrid trusses. The tubular steel, pins, and wood is what that's supported by. Now, I'm not sure, I don't want to criticize, but I have to. I'm not sure what that firefighter's doing. I'm not sure what the firefighter's doing in that position, but it doesn't appear to be a good tactical move. I can tell you that the first line pulled on this fire, okay, was what size? What size was the first line pulled on this fire? Not what you're supposed to pull.
I would guess 1 3/4.
An 1 3/4. Why is that? That's what they always pull. Okay? What do you think the second line pulled was?
The other 1 3/4.
The other 1 3/4. Absolutely right. So tactically, bad moves here. This firefighter's just doing his or her job here, but outgunned here. This is a waste of time right here. What's going on? You see that entire facade collapsed, and you see all these pieces of steel right here. Those are just these extended out like a slinky, right? The slinky's all the way stretched down is what that is. There's your hybrid truss that we looked at earlier that was supporting that, holding that up there. So severe hazard, not only floors and roofs, but anywhere these lightweight components are used and they're on fire, you don't want to be on them or under them when they're being compromised. All right, now to wrap all this up, I said it earlier that time is your enemy. So we're going to look at this chart, and then we're going to take another break, and we'll come back for session 3. This chart wraps up everything that we talked about. And I know you might not be able to read it from there, but if you can, I'll just give you a rundown. First of all, these first two, there's no ceiling. So what you have is a basement situation where fire impinges directly on the joist or whatever's being used as a joist. We don't have that here except in buildings under construction. So if you have buildings under construction that aren't drywalled in yet, and you have fire, there's probably not any people in them, and you probably don't want to be above that, fire, or if it's up in the attic below, because it's going to be directly impinging on what? The structural components. The structural components burning equals collapse. So we don't have this situation too much in our environment except under construction. So the rest of these are going down, and the floor joists, or in the case down here we have roof systems, are being protected by wallboard, drywall, except up here. Here's the one that Grandpop and Uncle Alvin fought the fires in right here. 2x10 floor joist, legacy construction, lath and plaster ceiling protecting those structural components. The finish rating is 74 minutes. And let's see, the firefighter protective membrane breach, 74 minutes before the fire breached the plaster and lath and started on those structural components. And the firefighter breached through, look at this, 79 minutes. That's why Grandpa and Dad and Uncle Alvin and them guys could operate in a structure of ordinary construction for an hour. This thing, intentionally they're burning this, and it is 80 minutes before the firefighter mannequin dummy that weighed whatever, 200-something pounds, breached through the floor. Okay? All right, now we're going to move away from that old building into the newer building, my house, and you're operating upstairs in the bedrooms, and there's a fire downstairs, and you're doing searches trying to save some people. Now we're looking at some wood I-joists here that the breach was 17 minutes, and in 26 minutes the firefighter fell through. Now, the fire started, the clock's ticking. The fire is reported, who knows how long that's been. The fire is dispatched. You respond to the fire, you set up for the fire, and you go in. Okay? We don't know when that clock starts. We have to judge it by what we're looking at when we get there and some other factors. But 26 minutes here, we're looking at this firefighter breaching through the floor. Let's see, metal gusset plates, 29 minutes. Finger joint, the glued one, 26 minutes. So you're in a 20 to 30 minute mark here on these type of systems. Here's your roof structures, and the roof with the 2x6 joists, roof rafters, and ridge board, that lasted 38 minutes. And the gusset plate truss lasted 23, so you lost 15 minutes here. So this is just a summary comparison that shows, here's how long it took for this to happen. So if you got drywall, it's going to fail fairly quickly, 16, 17 minutes in this range here. This one is longer time. Why? It's still drywall, but why is this one 44 instead of 26? That's almost 20 minutes difference, 18 minutes. Right there. It's a 2x10. It's not an engineered I-joist. It's not a truss. It's a 2x10. So the failure rate of the drywall is going to be fairly consistent. But for these structures to fail, right there, and like I said, you add all that time up, and you're arriving, and you got a few minutes to operate. So you need to be very wise, and your incident commanders need to be very wise on how long you're operating in these structures, okay? With that, we'll go ahead and end session 2, and we'll come back and finish up with session 3. Anybody have any questions at this point? Okay, good deal. Thanks a lot.